This is the first lecture on addition reactions of organic chemistry, addition reactions. So briefly, what we'll cover in this lecture is the addition of bromine. You'll discover this addition is unique because of the size and polarizability of bromine. Then we'll look at the addition of bromine in the presence of water or alcohols. These are other nucleophiles. So we'll see which ones, what the products should be. Next, we'll look at the mechanism for the addition of polar molecules such as Br and HCl to alkenes. Then we look at the real addition, some examples of the addition of HBr and HCl to alkenes. We'll also look at the rearrangement of carbocations. You will remember that we did carbocations as a reactive intermediate in one of the earlier lectures. And one of the characteristics of carbocations is that they readily rearrange to give more stable carbocations. So now we'll see the effect of the rearrangement in predicting the major product. We'll also look at the anti-Markovnikov addition of HBr. So in other words, we'll explain or refresh your memory on the Markovnikov addition of polar molecules to alkenes. And we'll look at the example of adding HBr, which is a polar molecule, how we can get an anti-Markovnikov addition. Lastly, we'll look at the addition of water to alkenes, also known as hydration. So let us begin. As I mentioned earlier, bromine is a large polarizable molecule. So if you look at your periodic table, you can see that the atomic weight there is 79. So it's pretty large. Because of its size, it is polarizable, which means that the electrons in bromine are shifting from region to region, creating, as you can see here, a partial positive end and a partial negative end to bromine. Since the alkene is nucleophilic, remember it has electrons, these electrons here will react with the positive end of bromine. Here's what's unique about this. This bond breaks, but it does not form an open carbocation as we would expect. The reason is that bromine is pretty large, so it's essentially sitting between these two carbons because of its size. Sitting between these two carbons, we call that the bromonium ion here. That's the bromonium ion. That's an intermediate, not a fully formed carbocation. But as you can imagine, these carbons here are in fact carbocationic-like. So what happens here is that the nucleophilic bromine, which came off from that initial addition in the rate determining step, will add to this carbon here that's more carbocationic-like. Why am I saying that? Is because this carbon here is more like a secondary carbocation compared to this one, which is more like a primer because it just got one carbon bonded to it here. So in other words, we will have the addition coming here. For this type molecule, however, it makes no difference because, as you can imagine, it can come in here also and you'll get the same product. But the main aspect here to observe is that the product is a trans addition. The two bromines will add to opposite sides of the carbon-carbon bond. So as you can see here, these type of reactions are described as stereo specific and regiospecific because they add to the alkene, and if you have a trans butene here, you will get this type compound. Notice the bromines are trans if written in this format here. And notice again that the methyl groups here are on opposite sides. That's why this becomes a meso compound. Remember, meso compound is a compound that has a plane of symmetry. Here is the cis butene. So again, the bromine will add to give a trans product, and you'll see here that the methyl groups are on the same side. Same side. And as you can imagine, it could add here, and its mirror image will be different. So therefore, this is a racemic type molecule. Let's review that again. So we have a chiral carbon here, which has 4 different groups around it. A chiral carbon here, which has 4 different groups around it. You can determine the R and the or S. Same here and here, and you'll determine that they are enantiomers, and it would be an equal mixture of enantiomers. Let's see if we can apply this concept here to linear free energy relationship that we've studied earlier. That's a mechanism or a systematic way to determine what type intermediates exist as the reaction proceeds from reactants to product. Specifically, what is the rate determining step? Is it positively charged? Is it negatively charged? So let's see, here is the experimental results, the Hammett plot for this reaction. Notice we're just putting here the substituent on one of the benzene ring. This is still being. So it's just on one, and here's our double bond right here. Bromine is added across it, and we're changing the substituent and measuring the rates. As you can see here, this is a negative slope, where this is electron, let's put it here, these are electron donating groups here, and over here these are electron withdrawing groups. So you have like your OCH3 over here, OCH3, and at this end, of course, hydrogen is right in the middle, and at this end you have your NO electron withdrawing groups, such as the nitro or the cyano. But let's look at this plot again. So notice there's a change in slope. So the OCH3, for example, favors the reaction. As you get less electron donating ability, the reaction rate slows down. So notice this slope is negative, which would imply that the intermediate is positive. Notice it changes slope, however, but still remains negative, but not the same magnitude here as we have here. This implies that there is a change in mechanism. Whenever you have a change in slopes, as we have here, there is a change in mechanism. So the mechanism for this portion of the reaction is different for this portion of the reaction because there's a change in mechanism. Let's see if we can explain that, or use that to explain and propose a mechanism. So what happens here? So here's our monosubstituted stilbene. Add bromine, we can get this, or we can get this, or we can get this. Let's see, if we got this one, this is favored by electron donating groups. So the OCH3 would favor the stabilization of that carbocation because that carbocation is adjacent to the OCH3. You can see down here, however, if we have electron withdrawing group, this is no longer favored to put the positive charge here, so it goes over to here where there is no electron withdrawing group adjacent to it to destabilize it. As you can imagine, here is what happens in the middle. So right in here, as you can imagine here, that's where there's not a big effect of the electron donating groups or the electron withdrawing groups. So we could look at this type intermediate here, where this could be hydrogen, for example, as the bridged intermediate, where this carbocation here is stabilized by the bromine. So no real substituent effect per se, because the bromine is actually assisting in the stabilization of the positive charge. So these would be the rate determining steps: RDS here and RDS here again, and of course RDS here again, and this would lead on to products, the different products. So what you've seen before is the rates of converting this still being to the products by varying X, the substituent on that particular benzene ring. So again, this is what I would expect for you to do if given a problem in which the experimental information was also given, and to see how we can utilize that experimental information to propose a reasonable mechanism. Notice we're saying propose because we're never quite sure what's happening in a beaker in terms of intermediates, but we do know that we cannot violate any of the chemical principles that we have discussed. Let us look at the addition of bromine in the presence of water, a good nucleophile. So as you can imagine, this is a double bond, nucleophilic. Here's bromine again, polarizable. So therefore we have one end is partially positive and one end is partially negative. Here's our bromonium ion. So this is, and of course the bromide. So in the presence of water, since water is a better nucleophile than the bromide anion, remember the bromide anion is pretty large. So if you introduce water, these electrons now are nucleophilic and can attack this carbon, as I mentioned before, because this carbon here is a more in this case is a tertiary-like carbocation, tertiary-like compared to this one, which is more of a secondary-like carbocation. So the preferential attack will be on this carbon here and not this carbon. And of course it's coming from the opposite side of the bromonium ion, because the bromine so large, it's on top blocking attack from that side. So the nucleophile would have to come from the opposite side. And as you can see here, this is the trans intermediate. Of course we still have two hydrogens on this oxygen, so we can take the bromide ion and create HBr, but this is the organic product, and notice it's a trans addition again. It's a trans addition. So we describe this reaction here as a stereospecific because it gives a trans addition, and it's regiospecific because this adds to a specific region of the molecule to give this. Adds to this carbon and not to the other carbon. So here's an example here. As I mentioned, these reactions are regiospecific and stereospecific. Regio means region of the molecule where the reaction occurs, specific regions. And stereospecific means taking a specific stereochemistry, well, forming a particular stereochemistry as a product. So here we have bromine in the presence of water. DMSO is typically used as a solvent because it will not react with that bromonium ion. So you can see here you get the trans product. Here's another example. This time the nucleophile is the alcohol. So hope you can see here that this alcohol will act just as water did in the previous slide. And again, it's a regiospecific reaction where this will add to this carbon, more tertiary-like, and the bromine will add to the other carbon, and again trans stereochemistry here. So you should be able to predict the stereochemistry of these reactions. Let us look at the addition of electrophilic addition of polar compounds. So we're looking at polar compounds here, the addition to alkenes. Let's first look at the mechanism before we look at specific reactions. So notice for this reaction here, our hypothetical reaction, we have an unsymmetrical or non-symmetrical alkene where this carbon here has two R groups and this carbon here has one and one hydrogen. So again, electrophile, E+, and here we have a nucleophile, electrons, forming a bond. We could form a bond here or a bond here. As we can see, here's a bond, new bond. If it forms over to here, this will be the carbocation right here. If it forms on this end here, as shown here, this will be the carbocation right here. But we can start seeing a little difference here. This carbocation here is a secondary, and this one here is a tertiary. So we'll get more into that in a second. In the next step, as you can imagine, this is a carbocation intermediate. So the nucleophile will react here to form this as the organic product, or it can react here to form this as the other organic product. So notice there are two possibilities here. If there is a alkene that's not symmetrical, it's not symmetrical, so we have a possibility of products. Let's look at some examples. So here we have this. Here's a double bond. Notice this double bond has a methyl group bonded to it, and over here it has a hydrogen right down here. As you can imagine, this will react with the electrophilic end of HCl, which is H+, to give the carbocation. As we pointed out earlier, there are two possibilities. This carbocation is a tertiary carbocation, and this one is a secondary carbocation. We'll see the importance of that in a second, because they have different stabilities. You can see here that, just to refresh your memory, tertiary carbocation is more stable than a secondary. So we'd expect this carbocation to be more stable than this carbocation. In the next step, as you can imagine, the Cl-, which is now the nucleophilic end of that other reactant, will react here to give this product. As you can imagine, this is the major product because it came from the more stable carbocation. We could rationalize that to mean that we have more of the tertiary carbocation because it's more stable compared to the secondary carbocation, which gives the minor product. So here are the two products, here and this one. So again, you should be able to predict the major and minor product based on the addition of a polar molecule to an alkene. This concept can be illustrated graphically as shown here. Energy. So in this region we have molecules or reactants that are intermediates, that's not stable. In the lower regions we have more stable, relatively more stable intermediates or reactants. So here is a reactants, same energy level, but one is going on to form the secondary carbocation and the other one goes on to form the tertiary carbocation. As you can see here, the tertiary carbocation is more stable, lower in energy than the secondary carbocation. So you'd expect more of this to be formed, hence more of that product. Notice again, this is the energy of activation for this tertiary, and this is the energy of activation for the secondary carbocation. So you can see that's a slow reaction compared to the tertiary. That's formation of the tertiary carbocation. Okay, let's look here at a rule that we have covered in undergraduate organic. It's the Markovnikov rule. So what Markovnikov did, a Russian chemist, what he did is he ran a bunch of reactions, and what he noticed that if you have an unsymmetrical alkene, such as this one here, this is a carbon with one methyl group and one hydrogen. This carbon here has two hydrogens. If you should add HX or HCl, it could be HBr also, this hydrogen here goes to the carbon that has the most hydrogen. So that's essentially Markovnikov's rule. that the hydrogen goes to the carbon that has the most hydrogen to give the major product. So it goes here, and of course the Cl will go over to here to give the major product, which is also known as the Markovnikov product. This would be the minor product. So you can predict the outcome of an addition of HX, HCl, or HBr to an unsymmetric alkene using Markovnikov's rule, where hydrogen will add to the carbon that has the most hydrogens, or you can work through the mechanism and see which intermediate is the most stable, or which carbocation is the most stable, and that carbocation would give you the major product. Let us look at this unique reaction here, or reaction with a reactant here. So let's see if we can rationalize what's happening here. If we had this alkene, of course we have two H's here, right? And we're adding HCl. You'd expect this to be the product. Where, well, no, you'd expect this one to be the product. Pardon me. So you'd expect here H to add over to here. And let me not use an arrow because I'm not moving, and arrows show the movement of electrons. So you'd expect that to add over to here to get this. And you'd expect the Cl to add here to get that. So that would be the expected product. But the bottom line is we do not observe that as the expected product. What's observed is that the Cl adds to this carbon and to this carbon here, and the H adds here. Because now that this was a CH and now it's a CH2. So the addition was completely reversed. Let's see why though. Let's first of all discuss this AlCl3. As you can expect, this is one of the reactions that's unusual. So we add a catalyst here. The catalyst is a Lewis acid. So again, it has a vacant orbital. So if you have Al and Cl and Cl and Cl, there's a vacant orbital here which can abstract one of these fluorines here to form a fluoride ion. So if you had fluoride ion here, let's look at F here bonded to C, F, F, and R, for example. You can see here that this would bond to this vacant orbital, leaving here R, C plus, and of course F and F. So it creates the carbocation by abstracting here a fluoride anion. You have seen that before when you looked at the Fidelkraft's acylation. The Lewis acid AlCl3 acts to abstract the fluoride anion into the vacant orbital. Another observation is that this CF3 here is electron withdrawing. As you can imagine, extremely good electron withdrawing, because we have a carbon with 3 electronegative fluorines bonded to it. So whatever this carbon is, it's going to be very positive. Very, 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 very positive. Okay, so let's see how we can rationalize this observation here. What's happening here is that the AlCl3 will create this. Again, so notice that this positive charge is distributed throughout these atoms here, from the carbon, because it abstracted one of these F's to create a positive, and we have 2 electrons here, so the positive charge is really distributed throughout these 3 atoms. As you can imagine, we can add here. So another way of writing this is like this. This would have to be a plus. This is another resonance structure here of writing this. Okay, so with this we can add HCl. As you can see, the Cl, the H, oh no, this means that this is adding here HCl. So the Cl is added to this molecule here to get this, and once we add now HF right across here, we can get this, and HCl right across here, we can get this. So once again, let me not confuse you. So what we have here is this A reactant here. The AlCl3 will abstract one of these fluorines to put a positive charge here. So what we're going to have is essentially CF2 positive. And if you draw the resonance structure here, you get this intermediate. So the other resonance structure would look like CF2 positive, okay, which is represented right here. Okay, then if you add a Cl to this, you're going to get Cl added here and this. If you add HCF to this double bond here, so again we're just adding here Cl minus, so Cl minus here, we'll add over to here to get this. Once you add your Cl minus here, you get this, and HF to get that, and adding HCl to this, you would get that. So bottom line is, to rationalize what we have seen before, to rationalize the observation, is that the AlCl3, a strong Lewis acid, creates this resonance stabilized carbocation. And of course the Cl can add to this end to get this intermediate, and the HF can add here, and HCl can add here to give different products, which is different from the expected, all because this group here is a strong electron withdrawing group. Okay, let's look at rearrangement of carbocations. Again, we have seen this before from an earlier lecture where we have carbocations as an intermediate. So let's quickly go through this. If you add HCl to this double bond here, you'd expect these two products. So Cl can add here to give this, or Cl can add here to give that product. What's not expected, however, unexpected product, is a Cl adding to this carbon. Of course, what happens here, you got to look at the mechanism. So HCl will give this as a secondary carbocation, has no choice. Well, it could add here, but this is the possibility for the secondary carbocation. This is secondary. If this is formed, as you can imagine, the migration of H with its electrons over to this carbon gives a tertiary carbocation with a more stable. You will recall from previous lectures, this is called a 1,2 hydride shift. Why hydride? Because we're moving H with its bonding electrons and leaving behind a carbocation. And of course, as you can imagine, what happens next is the nucleophilic chlorine attacks this carbon to give this as the unexpected product. So you should be able to utilize this concept to explain different mechanisms. Okay, let's look here at the addition of HBr again. If you add HBr to this is a Markovnikov product. But let us say you wanted the anti-Markovnikov product as the major product. So this is the anti-Markovnikov product because the bromine is adding to this carbon, which has only one hydrogen, and this has none. So we'd expect, if there were a Markovnikov, this hydrogen would add to the carbon that has more hydrogen. This has one and this has none. But this is the reverse. How can we get this product here as the major product? As you can imagine, the set of reaction conditions that's used before, i.e. just adding HBr, will not work. So we'll have to use something different. We add HBr in the presence of peroxide and heat. So this addition of a peroxide changes the mechanism quite a bit. Let's see how that happens. Peroxide, as you will recall from a previous lecture, is an intermediate. They are generally created by the homolytic cleavage of a bond, typically one example is an oxygen bond here. So what we have here, a homolytic cleavage where one electron goes here and the other electron goes here to form radicals. So remember, we have discussed radicals before. So what happens here is that this radical, being a reactive intermediate in the presence of HBr, as you can imagine, one electron, and the other electron goes onto bromine to form this interactive bromide atom or radical intermediate. Now that bromide atom or bromine atom will react with this double bond. But notice in this case, it's one electron. It has one electron already, so it just needs one electron from this double bond. So if we form a bond here to bromine, the other electron goes over here. Notice this is a tertiary radical. Of course, there's the other possibility. It can add here and put the radical here, but this is a secondary radical. Of course, you know where we're going with this. The tertiary radical is more stable, as we have explained in the previous lecture for the intermediates, than a secondary radical. So, and here's the trend. They have the tertiary radical more stable than the secondary radical. Why? As of course you know that, because we have alkyl groups here that have electrons that can help stabilize that one electron in that p orbital. I recall this is in a p orbital, and we have electrons here. Let's put hydrogens here. So these electrons here can stabilize that radical, which is not possible for the methyl. That's why it's the least stable radical. So with that said, the tertiary radical, which is more stable, will react with HBr. As you can imagine here, we have one electron coming out, this electron coming out to form this bond here, and a bromide radical. And notice that this is the more stable radical, and this would be the major product, and it's also the anti-Markovnikov product. The other radical here, this reacts here, one reacts here to form this bond here, and a bromide radical. This is the minor product. So you can imagine this is the major product because this is a more stable radical, and the more stable radical will form in the majority, which will give the major product. Of course, we still have some radicals floating around, so we know that radicals are intermediates. So to get the reaction to complete, the bromine radical can find another bromine radical to form more bromine, or the alkoxide radical can react with another bromine radical to form this as a product. So an example of the anti-Markovnikov addition, you will recall, is here's the alkene. Here's HBr, but in the presence of a peroxide and heat. You will recall a good example of a peroxide is benzoyl peroxide. This one where this breaks and that breaks to give the benzoyl radicals. That's enough. That requires just a little bit of heat, not too much, not too high a temperature, to break this bond right here, to give the, let me just draw it, to give the radical here, which looks like that, which you've seen before when we looked at radical intermediates. Okay, let's look here at the addition of water. So the hydration of alkenes, a hydration of alkenes. As you can see here, water is a nucleophile, fairly unreactive, but in the presence of a catalyst such as H+, we can have the addition of water across that double bond. So we have a cyclohexene, cyclohexanol. But in this case, which is a methyl cyclohexene, this double bond is not symmetrical because we have a methyl group here and we have a hydrogen here. As you would expect, the addition would be, because we have H, essentially HOH, this would be the nucleophilic end and this would be the electrophilic end. So following Markovnikov's rule, this is the major product here because this hydrogen will add to the hydrogen, the carbon that has the most hydrogen, and the OH essentially, we'll see that it's really H2O, will add to this carbon here to give the major Markovnikov product, and this is the minor product. I don't think I have a mechanism for this, but let's look at, let's look at this one. Where there is a rearrangement here. So this one here, this hydrogen can add here, and this OH can add here, or here and here. So we'd expect these two products here to be the expected product. However, it was observed that this is an unexpected product that was obtained where the OH here adds to this carbon, and it looks as if this hydrogen migrated. So you know exactly what happened here. It's again a rearrangement of a carbocation. So as you can see, whenever you have an intermediate that has the possibility of rearrangement, it's possible to get different products, which would, of course, as you can imagine, cut down on the yield for the expected product. Let's see the mechanism. So again, this reacts with the proton to give this carbocation here. Then this migrates over to here to create a more stable tertiary cation. And of course, as you can imagine, now the water reacts with this carbon. Notice it's not OH negative because the medium is acidic, so you will not find OH negative. So water attacks here, the nucleophilic portion, electrons, Lewis base, attacks here to get this. Two hydrogens bonded to oxygen, which is bonded here, has a formal positive charge, and of course we can take that off to get the catalyst again, and this is the unexpected product. Here's a similar reaction, and notice again that this carbon, it appears that this OH from the water is bonded here, and this methyl group is down here. So obviously the unexpected product came about because a carbocation intermediate was formed, and in this case we have a methide migration, a CH3 with its electrons, notice with its bonding electrons here migrating. So let us look at the mechanism. So we got protonation here to give this. Here's the methide with its electrons moving over to here, and water comes in, and of course the loss of proton here, and this is the unexpected product. So again, you should be able to propose a mechanism which is consistent with the experimental observation. The experimental observation here is that this is the unexpected product. How do you explain it? Of course, as you can imagine, this is the RDS for that reaction because it creates the intermediate, and it's the slowest step in terms of destroying a neutral molecule here to form an intermediate. Let us see if we can apply that concept here. So propose a mechanism. Notice a reasonable mechanism. Why reasonable? Because we really do not know the exact mechanism, but we can propose a mechanism that's reasonable based on our knowledge of chemistry. So here's the reaction. Addition of HBr. You'd expect the addition to occur here, and if it were a Markovnikov addition, which it should be because there are no peroxides present, you'd expect the bromine to be here and the H to be here. but the product is actually this. So a couple observations here. The first is that this unexpected product, the bromine doesn't add to the carbon here. The next observation is that this 5-membered ring has now expanded to a 6-membered ring. The reaction is right here. So let's see, how can we propose a mechanism to account for this ring expansion and this unexpected product? So the first step, as you can imagine, is the nucleophilic electrons here, the nucleophilic end of the molecule here, reacting with the partial positive end of this molecule here, which is really the H. We get a carbocation. One would say, gee, we could get a carbocation here, but if you got a carbocation here, it would not give you the product that was observed. So let's put the carbocation here, secondary, and we can now expand by moving a bond migration from here up to here to give this. So notice again, it's secondary going to a secondary, and that's okay because it assists in the explanation of this product, and that's why we say in a proposed mechanism, a possible mechanism. So this is our secondary carbocation based on this bond migration 1 2. It's moving from here to here, 1 2 bond migration to create this carbocation here. And of course the bromide nucleophile can now react to give this as the product, and this is in fact the unexpected product based on this ring expansion right here caused by the bond migration. I think this is the last slide, and it is. So this is the first lecture of the addition reactions. We have I think a couple more which I'll post before the week is out, so be on the lookout for those, but continue reading on this. The next chapter will be elimination reactions, and the last chapter will be pericyclic reactions. So start reading up on those, and I'll get those lectures out before too long. Okay?